In this video, we are going to solve questions on thermochemistry. Okay, so we are using the tutorial sheet from Unidas. Okay, so this is for second semester students who are doing their pre-meds. Okay, and if you're doing any NS, pre-med, or A-level chemistry, you will come across this topic, which we are calling as thermochemistry. Okay, so we are going to solve a lot of questions on thermochemistry. So you can see here we have questions on the first law of thermodynamics. Okay, we have a lot of questions in this tutorial sheet. So all these are the questions that we are going to do to solve. All right, so for you to access the full video, kindly register with us. Our tuitions are just 150 per course per month. All right, so let's get to the solving. So we are going to solve these questions one by one, each one of them. Okay, we are going to solve them. So the first one there, they're saying define energy, kinetic energy, potential energy, and internal energy. So I've written down the definitions for you. So the energy is simply the capacity to do work or to transfer heat. Okay, so that's how we can define energy. And then when we talk about kinetic energy, okay, this is just the energy due to the motion, okay, of the particles in a system. Okay, so the energy due to the motion of the particles in a system is called as the kinetic energy. Okay, and it is calculated by this formula where we are saying kinetic energy is equals to 1 over 2 multiplied by mv squared. Okay, so this m here represents the mass, and then this v here represents the velocity. Okay, so that's how we can calculate the kinetic energy. Okay, what about the potential energy? So the potential energy is the energy due to the position or configuration, okay, such as the gravitation. Okay, so it's given by the formula potential energy is equals to mgh. Okay, so this m is the mass, this g is the gravitational acceleration, okay, and then this h here is the height above a reference point. All right, and then now we can talk about the internal energy. So the internal energy is just the total energy within a system. Okay, so the total energy within a system will include one, the kinetic energy of the particles, and then two, it will include the potential energy, okay, due to the molecular interactions of the what? Of the particles. Okay, so this is how we can define these four types of energy that we can see on our screen. Okay, so that was question number one. We go to question number two. Okay, they're saying the energy, they're saying the internal energy of a substance is a state function. Okay, what does this mean? Okay, so they're simply asking us to explain what this state function is. Okay, so in my explanations, I was saying state functions are properties that describe a system's current state. Okay, regardless of how the system got to that state. Okay, so the key characteristics under state functions include include the following. The first one is that the path, okay, or the state functions, okay, it only depends on the current state. Okay, so dependence on the current state only. Okay, and then it is independent from the path or the process taken to reach that state. Okay, and then the other thing is that it will have a unique value for a given state. So examples of the state functions include the internal energy that we just defined, the temperature, the pressure, the volume, even the enthalpy. All these are state function. Okay, so let me just explain more about what a state function is. All right, so we are saying that, okay, we are saying that a state function is a property, okay, that depends only on the current state and not the path taken to reach that state. Okay, so for example, your location. Okay, I'm going to give an example of a location. Okay, so right now, wherever you are, okay, that's your location. So the location that you have, okay, is it only depends on the current state, okay, where you are, and it does not depend on the path that you took to reach that location. Let me even give an example. Maybe you are at East Park, okay? So let's say you are at East Park. So the location that you are at East Park, okay, does not depend on the path that you took to reach this East Park here, okay? It does not depend on that, okay? It's independent of the path. It only depends at the current position where you are, which is what? East Park. So you can get to this East Park in a number of different ways, okay? You can board a bus, you go to East Park, okay? You can maybe drive yourself there using a car, you get to East Park, you can walk, you can also get to East Park, okay? So either you come by bus, you come by your own car, or you walk, okay? When you are at when you are at East Park, your location will just be what? East Park. So it does not matter the path that you take to reach this destination, which is East Park, okay? When you're at East Park, we are going to say your location is East Park, okay? We're not going to say your location is bus East Park because you took a bus to come to East Park. No, okay? So that's the state function. It only depends on the current state, but does not depend on the path that you take to reach there. Okay, so let me also give an example of something that will not be a state function. Okay, so for example, distance. So I'm just using this distance and location to explain the concept of state functions. So distance is not a state function. Okay, distance is not a state function. Why? Because distance depends on the path that you take. Okay, depends on the path that you take. Okay, so the total distance that you are going to travel to reach your current location, okay, would depend on the path that you take. Okay, so let's say, for example, this is the East Park where we are going, right? Okay, this is the East Park. So the distance from where you are to this East Park here, okay, would depend on the path that you are going to take. Okay, so you can take maybe a shortcut. Okay, that shortcut, maybe it can be, let's say, 1 kilometer. Okay, or maybe you can first start by going like this, going like that, and then you go to East Park now. Okay, so the distance that you would have covered here maybe to be 3 kilometers. Okay, and then you can also maybe use another road. Okay, that is a bit shorter. You go like that, you go like that, and then you reach East Park here. Maybe you take 2.5 kilometers. Okay, so you see that the distance that you're going to travel from your current location here to this East Park here, okay, would depend on the path that you're going to take. Okay, if you take the shortest possible path, you can reach East Park in 1 kilometer. Okay, if you take maybe a longer distance, okay, it can take 2.5 kilometers, just like that. Okay, so if something is not a state function, it means the current state, okay, will depend upon the path that you are taking. But something is a state function if does not depend on the path. And I gave an example of this location here. So when it comes to chemistry now, okay, you have to give the actual examples. Don't give our location as an example. No, I was just using it to explain. So you say internal energy is an example of a state function, okay? Because it doesn't matter the path that you take, you are still going to reach the same internal energy, okay? Even the temperature, the pressure, the volume, and the enthalpy, okay? So those are examples of state function. And then on the other hand, okay, we have these non-state functions like work, heat, okay? They depend on the path taken and are not unique to a specific what? State. So I've explained that. So we go to question 3 now. So question 3, they're saying what property of enthalpy, okay, provides the basis for Hence's law? Okay, and then they're saying explain. All right. So the property of enthalpy that provides the basis of Hence's law, okay, is the state function. So the same thing that I'm from explaining, okay, is the one that provides the basis of Hence's law. Okay, so what does that mean? Okay, it means that the change in enthalpy, okay, because we're talking about enthalpy, means the change in enthalpy, okay, depends only on the initial and final states of a reaction, okay, and not on the path or the series of steps taken to reach that final state. Okay, so we can even state what Hence's law states here. We can say Hence's law states that the total enthalpy change of a reaction is the sum of the enthalpy changes of individual steps, okay, allowing enthalpy changes for complex reactions to be calculated using the what? The simpler reaction. Okay, so in most of the questions, you'll be given simpler reactions, okay, and then from the simpler reactions, you'll be asked to calculate the enthalpy change of a more complex reaction. Okay, so we are going to be calculating such enthalpies, okay, by using what we call as the what? The Hence's law. Okay, so we are going to look at questions as we go on and solve this tutorial sheet. All right, so now we go to question 4. Okay, so this one here involves more of the solving than the explaining. All right, so let's solve it. Okay, let's solve it. So we are saying that, okay, when 1.0 moles of nitroglycerin, okay, decomposes, it causes a violent explosion and releases, okay, 5.72 multiplied by 10 to the power 3 kilojoules of heat. And then they have given us the reaction here. Okay, so we have this big compound here decomposing into carbon dioxide, water, oxygen, and nitrogen. Okay, so the first question here is that, is this reaction exothermic or endothermic? Okay, so what can we say there? So we're going to say one, that reaction is exothermic. Okay, so why is it exothermic? Because in the question they are saying it causes a violent explosion and releases. Okay, so this word releases here is a key word. Okay, meaning it's giving out heat. Okay, so we know that when a reaction gives out heat, okay, then it's what? Exothermic. Okay, so we are going to say this reaction here is exothermic. And then the next question is draw an enthalpy diagram for it. Okay, so we know that for exothermic reactions, the enthalpy diagram is like this. Okay, let me draw it a bit straighter. Okay, so we know that on the vertical axis here, we are going to have our enthalpy. Okay, our change in enthalpy is going to be in the vertical axis. And then on the horizontal axis, we are going to have the progress of the what? Of the reaction. Okay, we're going to have the progress of a reaction. So in an exothermic reaction, okay, the reactants are always at a higher temperature, not a temperature, the reactants are always at a higher enthalpy than the products, okay? So why? Because in this reaction, we are going to be releasing energy, okay? So the reactant had a lot of energy, so we can show it by drawing the reactant at a higher height here, okay? So let's say these are reactants, and then the reaction takes place like that, and then it goes on and forms the products like that. So we can see that these reactants here will be at a higher enthalpy than the products that will be there. Okay, all right, so we are going to say here on the reactants, we have C3, H5, then we have NO3, and then 2 like that. So this is the reactant, and then it decomposes, okay, to form what? Carbon dioxide here, plus 5/2 water, plus 1/4 oxygen, then plus 3/2 nitrogen, like that. So these are the products that there is the what? The reactant. Okay, so we are seeing that these reactant here are at a higher enthalpy than these products here. So if I can draw a line here, straight like that, okay? So this energy here, from the energy of the reactants to the peak, okay, of this curve here, this energy here, we are going to be calling it as the what? Activation energy. Okay, so the activation energy is simply the energy that you need in order for a chemical reaction to do what? To take place. All right, and then the difference, okay, the difference between the enthalpy of the reactants and the enthalpy of the products here, it will be our change in enthalpy. Okay, so this energy here that I've shown in yellow, we are going to say this here is our change in enthalpy. So we're going to say this is equals to, okay, we've been given the value there, which is 5.72 multiplied by 10 to the power 3. So when writing it here, we're going to write it as a negative. Okay, why? Because energy is being released by the system, okay, times 10 to the power 3 kilojoules of heat. Okay, so we're going to put this negative here because energy is being released to the surrounding. Okay, so this is the enthalpy diagram, okay, for this exothermic reaction. All right, so we are done with that one. We go to question number 5. Okay, so question number 5, they are saying a layer of copper welded to the bottom of a skillet weighs 125 grams. How much heat is needed to rise the temperature of the copper layer from 25 degrees Celsius to 300 degrees Celsius? Okay, the specific heat capacity of copper has been given to be 0.387 joules per grams Kelvin. All right, so here we just want to find how much heat is needed. Okay, so that how much heat needed is found by, okay, this Q here represents the heat. So we are going to say heat needed is equals to mass multiplied by specific heat capacity multiplied by the change in temperature. Okay, so let's calculate. Okay, so the mass we've been given, it's 125 grams. Okay, what about the specific heat capacity? We've been given 0.387 joules, okay, per gram Kelvin. Okay, and then what about the change in temperature? Okay, so the change in temperature, we are going to subtract the final temperature, which is 300, minus the initial, which is what? 25. If you want, you can first change this 25 to kelvins, okay, by using this formula. Kelvins is equals to the the temperature in degrees, okay, plus 273.15. Yes. So you can first convert this here and this 300 here to kelvins, and then you subtract them. Okay, but the difference between those temperatures, okay, will be the same. Okay, the difference will be the same. Either you are using the kelvins or the degrees Celsius. So we are going to say 300 minus 25. Okay, so what will this give us? Okay, it's going to give me a 275. All right, so this is uh the change in temperature. Okay, so now we can find how much heat was needed to raise that temperature. So we're going to multiply 125 multiplied by, okay, this C here is 0.387 multiplied by the change in temperature will just be 275. Okay, so this is going to be equals to, so you get this value punch on your calculator. Okay, so I'm getting 13,318.125 joules. Okay, so we can even put this heat in kilojoules. So we divide everything by 1000. Okay, when you divide this number here by 1000, okay, to put it in kilojoules, we are going to get 13.3. Okay, I can round it off to, I can round this 8, okay, to this one to be 2, and then that will be kilojoules. Okay, so this here will be the amount of heat needed to raise the temperature of that copper layer from 25 degrees Celsius, okay, to from 25 degrees Celsius to the 300 degrees what? Celsius. All right. All right, so now let's look at the next question, which is question 6. Okay, so this one here, we are going to solve it in a similar way we did with question 5. Okay, so the question reads, they're saying find the heat transferred in kilojoules when 5.5 liters of ethylene glycol with the density of 1.11 grams per milliliter, okay, in a car radiator cools from 35.0 degrees Celsius, okay, to 25 degrees Celsius. Okay, so for us to find the heat that has been transferred, we're going to use the same formula. Okay, so heat is equals to MC multiplied by the change in temperature. Okay, so I don't know why here they didn't give the specific heat capacity of this guy. Okay, but I'll give it to you. So we are going to say, what do we have here? Okay, we know that we have to find the mass, but the mass, we do not know it. Okay, and then the specific heat capacity of ethylene glycol, okay, is simply 2.42, okay, joules per grams Kelvin, like that. Okay, and then we also need the difference in temperature. Okay, so this difference in temperature, or the change in temperature, is found by subtracting the final temperature, okay, minus the initial temperature. So here they're saying this radiator cools from 35 to 25. So meaning our final temperature is what? 25. Our initial is 37. So the change in temperature is 25, which is the final temperature, okay, minus the 37 there. So if I find the difference there, I'm going to find is it a minus 12? Okay, I'm going to find minus 12 as my difference in temperature. Okay, so how can we find this mass here? So we can see that from the question, we've been given the volume and the density of this ethylene glycol. Okay, so we can use this density and this volume to find the mass of this ethylene glycol. So we're going to say density is equals to mass over volume. So meaning that mass is equals to density multiplied by volume, right? All right, so we're just going to multiply. So the density there is in grams per milliliter, and then this volume here is in liters. So we have to convert that volume first of all to milliliters. So we are going to say volume is equals to 5.50 liters. So let us convert this volume to milliliters. So to convert that, we are just going to multiply this by 1,000, like that. So we are going to get that our volume will just be 500 milliliters. Okay, so now we can place it into this formula. So the density is 1.11 multiplied by the volume, which is 5500. Okay, so when we multiply this, what are we going to get as our mass? Okay, so mass is going to be equals to, okay, so when I multiply this, I'm getting 6050 grams. Okay, so this here will be the mass that I'm going to use. So I'm going to put it here. So 6050 grams. All right, so now we can replace the quantities that we've come up with. Okay, we can replace them into the formula for the heat. All right, so we're going to say this heat is equals to the mass, which is 6050 multiplied by the specific heat capacity, which I gave you as as 2.42 multiplied by the change in temperature, which is what? Minus 12. All right. So this here is going to give us what? Okay. So when I multiply this, it's going to give me a minus 17,600 joules. Okay. So that is my answer there. But remember, they said the answer should be in kilojoules. So we have to divide this number by 1,000. Okay, so I'm going to get minus 176 kilojoules. Okay, so here, this is the energy that was transferred, okay, when the car radiator cooled from 37 degrees Celsius to 25 degrees Celsius. Okay, so this value is negative here because heat was being lost from that radiator. Okay, no wonder it's cooling here from 35 to 25 because heat is coming out of that radiator. No wonder we are seeing a negative sign in front of this heat, okay, meaning it's coming out like that. All right, so that's how we solve our question number 6. Okay, that's how we solve question number 6. All right, so now we can go to question number 7. Okay, so this is our question number 7 here. So the question 7 reads, you place 50 milliliters of 0.5 molar sodium hydroxide in a coffee cup um, calorimeter, okay, at 25 degrees Celsius, and you carefully add 25 milliliters of 0.5 molar hydrochloric acid, also at 25 degrees Celsius, okay. After stirring, the final temperature, okay, is 27.21 degrees Celsius. Calculate the heat of the solution, which is the Q solution that you are seeing there in joules, and calculate the change in enthalpy of the reaction, okay, in kilojoules per mole. Assume that the total volume is the sum of the individual volumes and that the final solution has the same density and specific heat capacity as water. Okay, so to find the heat of the solution, which is Q, and then solution there, okay, we are going to use the formula, okay, the normal formula that we've been using, which is M multiplied by capacity, specific heat capacity there multiplied by the change in what? Temperature. And then to find the change in the energy of the reaction, okay, this change in the energy of the reaction will be given by the heat of the solution divided by, okay, the moles of the moles of the limiting reactant, okay, from the reaction of the, we can just say for of the reaction there. Okay, so for us to calculate the heat of a solution, we need the mass of the solution, we need its specific heat capacity and the change in temperature. Okay, and then to find the change in the heat of the reaction, we just divide the value that we are going to get here with the moles of the limiting reactant from the reaction that is occurring in this system here. Okay, so we have sodium hydroxide reacting with what? Hydrochloric acid there. Okay, so we're going to find the limiting reactant between those two solutions. Okay, so the first step is to determine the total volume, okay, and the mass of the solution. So how are we going to do that? Okay, so the total volume, we're just going to add the volume of the sodium hydroxide, which has been given as 50 milliliters, plus the volume of the hydrochloric acid, which has been given as 25 milliliters. So when I add this, I'm going to get 75 milliliters as my total volume. Okay, so it means this is the volume of the solution that has been formed when I mix this hydrochloric acid and the sodium hydroxide. Okay, so how can I find the mass? Okay, so when you come at the end here, they've said this solution has the same density as water, which is just 1 gram per milliliter, and it also have the same specific heat capacity as water. So for us to find the mass, we know that density is equals to mass over volume. So we have the volume of the solution. We have also been given the density from the question. So for us to find the mass, we're just going to say mass is equals to, okay, mass is equals to density multiplied by volume. So our density is 1 multiplied by the volume, which is 75. So we're going to find that our mass is just what? 75 grams. Right. So we have the mass, we have the specific heat capacity. We are remaining with the what? The change in temperature. Okay, so let me create some space here and then we can calculate the change in temperature. Okay, so I'll put my mass here. So my mass is 75 grams. My specific heat capacity is 4.184. Okay, so now how do we calculate the change in temperature? Okay, how do we calculate the change in temperature? So remember, okay, these two solutions that we are mixing, they were both at what? 25 degrees Celsius. Even this one, 25 degrees Celsius. And then after the reaction has happened, okay, it's like you have uh, sodium hydroxide here, okay, which is at 25 degrees Celsius. And then you add an acid here, which is hydrochloric acid, which is also at 25 degrees Celsius. And then once this hydrochloric acid and the sodium hydroxide react, okay, the result of this solution here, the resulting solution has a temperature of 27.21 degrees Celsius. Okay, so that means that 27 there is the final temperature. So we're going to say the change in temperature is just 27.21 minus, okay, 25. And then when I subtract this, what do I get? Okay, I'm going to get 2.21 as my change in temperature. Okay, so now I'm put my change in temperature here. So my change in temperature is just 2.21. So I have everything that I need in order to find the heat of the solution. So we are going to say Q of the solution, or heat of the solution, is equals to mass 75 multiplied by specific heat capacity multiplied by the change in temperature, which is 2.21. Okay, so when I multiply this on my calculator, I'm getting approximately 693.4 joules. Okay, so we've answered the first part of the question. Okay, we've answered the first part of the question where they told us to calculate the heat of a solution in joules. Okay, so now what is remaining is the change in enthalpy of a reaction. And we said we are going to use this formula here. So we already have the heat of a solution. Now we have to find the moles of the limiting what? Reactant. Okay. So for us to know the moles of a limiting reactant, okay, it means we have to know the mole ratio of the reactants that are involved here. Okay, so let me write my Q solution somewhere here. So my Q solution, we found it was 693.4 joules. Okay. And then now, in this case, we have sodium hydroxide plus hydrochloric acid. These are the two that are reacting. Okay. So we know that a reaction between a base and an acid will always give you what? A salt. So the salt here is sodium chloride plus water. So you check if this equation here is balanced, okay? And it turns out that this reaction here is balanced already. Okay, so meaning the mole ratio of sodium hydroxide to, let me show it in a different color. The mole ratio of sodium hydroxide here is 1:1 with the hydrochloric acid. Okay, so let's calculate the moles of sodium hydroxide. So how are we going to calculate these moles of sodium hydroxide? Remember, we've been given the volume and the what? The molarity there. So remember, we used to say molarity is equals to volume. We used to say molarity is equals to moles over volume. So now we're finding these moles. So moles is equals to mv. Remember this formula, okay? And then we said that this volume here should always be in what? Liters. So how do we convert that 50 milliliters to liters? We divide it by 1,000. So we are going to say m is 0.5 multiplied by 50 divided by 1,000, like that, to convert the 50 milliliters to what? To liters. So when I find the moles of this guy, okay, when I find the moles of this guy, I'm going to find 0.0250 moles. Okay, so what about the moles of hydrochloric acid? So moles of hydrochloric acid will just be equals to, okay, we have 25 milliliters of 0.5 molar. So the molar is still 0.5 multiplied by 25 divided by 1,000, like that. Okay, so this is going to be equals to 0.0125. Okay, so now how do we determine which one is the limiting reactant? Okay, so the one with the fewer moles, okay, or the smaller value for the moles will be our limiting reactant. So the hydrochloric acid here becomes the limiting reactant because the mole ratio of the sodium hydroxide and the hydrochloric acid is just 1:1. Okay, so the one with the fewer moles is our limiting reactant. So to find this change in the heat of a reaction, we're going to divide Q solution, okay, divided by the moles of a limiting reactant. And we see that the moles of a limiting reactant will be these here, the 0.0125. Okay, so let's find down. Okay, so we're going to create some space here. Okay, so let's calculate the Q, I mean the change in the energy of the reaction. So the change in the energy of the reaction will be equals to Q solution, which is 693.4 joules, divided by, okay, so this is joules, divided by 0.0125 moles. So this is what I have. Okay, so punch this onto your calculators. I'm getting what? Okay, so when I punch that into my calculator, okay, I'm getting um five, five, okay, five, and then zero joules per mole. Okay, but remember here they said we should put our answer in what? Kilojoules. So we are going to divide this by 1,000. We are going to remain with 55.5 kilojoules per mole. Okay, so this here is our change, okay, in the enthalpy, or our change in the energy of the reaction. Okay, so that's how we calculate question number, that was question number 7, right? Okay, so that's how we calculate question number 7. All right, so since this energy is being lost, okay, since this energy is being lost, we include a negative in front of this energy of the reaction. Okay, so this here will be our correct answer there. Our final answer will be minus of 55.5 kilojoules per mole. All right, so now let's look at question number 8. Okay, let's look at question number 8 here. All right, so question number 8 reads, they are saying a manufacturer claims that its new dietetic dessert has fewer than 10 kilocalories per servings. Okay, to test this claim, a chemist at the University of Lusaka's chemistry laboratory places one serving in a bomb calorimeter and burns it in oxygen. Okay, so the heat capacity of the calorimeter is 8.15 1 kilojoules per Kelvin. The temperature increases by 4.937 degrees Celsius. And then the question now is the manufacturer's claim correct? Okay, so the manufacturers are claiming that this new dietetic dessert has fewer than 10 kilocalories what per serving. Okay, so how are we going to prove that claim? Okay, so we need to calculate the total energy released during the combustion of the dessert serving and compare it to what? To 10 kilocalories there, what that we've been given. Okay, so their claim is that we are going to produce less than this. Okay, so is it true? So we need to calculate it. So remember, we're going to say heat, okay, or the amount of energy produced. In this case, since we are using a bomb calorimeter here, okay, there's no need for the mass. Okay, we're just going to say the heat capacity multiplied by the change in temperature, like that. This is the formula that we're going to use in order to find uh, the energy, okay, that comes from this diet. Okay, so our heat capacity here has been given as 8.151 kilojoules per Kelvin. Okay, what about the change in temperature? Okay, so they're saying the temperature increases by this. So meaning this same thing here that we have is the change in temperature. Okay, so 4.937 uh, degrees Celsius. Okay, so let's find the energy. Okay, so the energy will just be equals to the heat capacity, which is 8.1. Okay, 8.1 um 8.1 51 multiplied by the change in temperature. Okay, so the change in temperature is always the same. Okay, either you have degrees Celsius there or you have Kelvins, the temperature is there. The difference of the temperatures is always the same. So we're going to use the same 4.937. Okay, so when I multiply this, what will be the value of the energy that I'm going to get? Okay, so I'm getting 40.23, okay, kilojoules. So that's the energy that I am what? I am getting. Okay, so this energy, what we notice is that it is in kilojoules. So we have to convert this energy into kilocalories. Okay, and then we can compare it with the 10 there. Okay, so I'm going to erase this part. So we know that 1 calorie, okay, is equals to, okay, is equals to 4.184 joules. Okay, but here we have kilocalories here, and then we also have kilojoules here. So if I multiply this side by 1,000, okay, if I multiply this side here by 1,000, I'm going to get 1 kilocalorie. Okay, so I'm going to get 1 kilocalorie. Okay, so this K here, remember from our unit conversions, okay, metric table, we said it means 1,000. Okay, so 1K calories is the same as 1,000 calories is equals to, okay, since I multiplied by 1,000 on the left here, I'm also going to multiply by 1,000 on the right hand side. Okay, so when I multiply by 1,000 there, what am I going to get? Okay, so let's multiply on the calculator. We have 4.184. Okay, 4.184 multiplied by 1,000. Okay, so I'm going to get 184 joules. Okay, or we can just write it in terms of the thousand, right? So we can say 1 kilocalorie, okay, is equals to, if I multiply this by 1,000, okay, how can I write this number so that the 1,000 is not shown? Okay, I'm just going to say this is same as 1.184 kilojoules. We know that this kilo here, this K, represents what? 1,000. So we're going to use this conversion factor to convert this 40.23 kilojoules to kilocalories. Okay, so let's convert now. So we're going to make some space on top here. So we're going to say this energy from the new food, okay, is just going to be equals to, I have my 40.3, 0.23 kilojoules, and then I'll multiply by, okay, 4.184 kilojoules. So I'm using dimensional analysis, and then one I have on top there, I'm going to have 1 kilocalorie like that. Okay, so I'm just using dimensional analysis. I hope you haven't forgotten your semester 1 work. So the kilojoules and the kilojoules is going to cancel. So what am I going to remain with? Okay, this 40.23 multiplied by 1 divided by 4.184. Okay, so when we divide that, I'm going to get 9.62 kilocalories like that. Okay, so we see that the energy that we get from this new dietic dessert is 9.62. Okay, and then when we compare it to the 10 that we had there, okay, when we compare the 10 that we had there, we see that this 10 is bigger than the 9.62. So meaning their claim that it is fewer than 10 is actually what? True. So we're going to say the claim is true. All right, so that's how we can solve question 8. Okay, we are done with question 8. We can now go to question 9. Okay, let us now solve question number 9. Okay, let us solve question number 9. So question number 9 reads, a 50.0 gram sample of water at 100 degrees Celsius was placed in an insulated cup, and then a 25.3 gram of zinc, which was at the temperature of 25 degrees Celsius, was added to the water. The temperature of the water dropped to 96.68 degrees Celsius. What is the specific heat of the zinc? Okay, so here we have to understand the question. Okay, so we need also to understand the energy transfer. Okay, because we have two things there. Okay, we have this water, okay, which is in this bowl here at 100 degrees Celsius. And then to this water, we add zinc. Okay, so let's say this is our zinc that we are adding there. Okay, we add this zinc, and this zinc here is at 25 degrees Celsius. Okay, so after adding zinc to this water, we are told that the final temperature of this water plus the zinc is now what? 96.68. Okay, 96.68 degrees Celsius. Then they're asking us what is the specific heat of zinc. Okay, so what are we going to use there? We're going to use the energy transfer. Okay, so when you put the zinc in the water, okay, energy is transferred from the water that is at a higher temperature to the zinc that is at the lower temperature. Okay, so we are going to say the energy, okay, or the heat that is lost by water is equals to, okay, the energy that is gained, okay, by the zinc. All right, so these two here are going to be equal. So how can we find the specific heat of zinc? Okay, so we start first with the water. So for us to find the specific the heat lost by the water, we need to multiply the mass of the water multiplied by the specific heat capacity of water multiplied by the change in temperature of the water. Then this is going to be equals to the mass of the zinc multiplied by the specific heat capacity of the zinc. That's what we want to find. And then multiplied by the change in temperature of the what? The zinc. All right. Okay, so from there, what are we going to do? Okay, so from there, what are we going to do? We are going to get the data that we've been given in the what? In the question. Okay, so we are going to get the data that we've been given in the question. So we're going to say the mass of the water is just what? 50 grams multiplied by the specific heat capacity of water. Okay, we know its value. Okay, it's just 4.184 multiplied by the change in the temperature of the water. So the initial temperature of the water was 100, and then it has reduced to what? To 90. It has reduced to 96.6. It has reduced to 96.68. So it means this is the final temperature. Okay, so the change in temperature will just be equals to 96.68 minus 100. Okay, so when we subtract this, what are we going to get? We're going to get minus 3.32. Okay, so this here is the change in temperature. So minus 3.32 like that. Okay, why? Because energy is being lost there. No wonder it's negative. Okay, so this here should be equals to the mass of the zinc, which is 25.3, multiplied by its specific heat capacity. Okay, I mean the specific heat of the zinc that we want to find. Okay, and then multiplied by the change in temperature of the zinc. So the initial temperature of the zinc here is 25. Okay, and then the final is this 96.68. So the change in temperature will be 96.68 minus 25. So when I subtract this, okay, what am I going to get? I'm getting 71.68 as my change in temperature. So I'll put it here as my change in temperature, 71.68. 8 like that. All right, so from there now we can calculate the C2 there, which is the specific heat capacity for the zinc. Okay. By the way, I forgot to add a negative on one of these side. Okay, so you can either add a negative here, okay, or you can add a negative here. Well, so why are we adding a negative on one side? Because one of them is losing the energy. Okay, so what is losing the energy? It is the water. So we are going to put a negative here. If you want, you can put it there. There is no problem. So the energy of this water is being lost. So I'm putting a negative. Okay, and then this guy here is receiving the heat. So it should be positive like that. Okay, so let's find this C2 here. So it means all this here is being multiplied by what? A negative, because this water is losing, okay, the energy. So when I multiply whatever I have on the right here, okay, what am I going to have? So when I multiply all this, I'm going to have minus 694.54. Okay, remember I have a negative outside is equals to, and then here, if I multiply 25.3 multiplied by 71.68, what am I going to get? I'm getting 1813.50. Okay, and then multiplied by C2. So this C2 is the specific heat capacity of zinc that we want to do what? To find. So let's find it. Okay, so cleaned on top here. So we are going to say C2 is actually equals to, if I multiply this negative and this negative, I'm going to have a plus. So it will be 694.54 divided by 1813.50. Right, so when we divide this, what we're going to find as our specific heat capacity of zinc, we're going to find 0.383 joules, okay, per grams Kelvin, like that. So this one here will be the specific heat capacity of our what? Our zinc. So we've used the concept of the what? Of the energy transfer or the heat transfer. So the heat transfer was traveling from the water to the zinc. Okay, so that's how we do with question 9. We go to question 10. Okay. All right, so question 10, they're saying um use the bond energies, okay, to calculate the change in enthalpy for the reaction of methane with chlorine and fluorine there, okay, to give freon. Okay, so freon 12 is just this compound here that is given by F2Cl2. Okay, check the literature for the bond energies. Okay, so you can check your zoom there. Okay, at the end there, you find the bond energies. Okay, so what we need to do here is write the structural formulas of all these compounds that you can see here. Okay, so the first one here is methane. So methane, we can write it as C bonded to 4H, okay, to 4 hydrogens like that. And then we are adding this to 2, okay, and then I have in the brackets I have Cl connected to Cl like this. Okay, and then plus, here I have 2F, so it means 2, then in the brackets I have F being connected to F. Okay, and then on the other side, I'll say this produces, okay, I'll just write them down here. So this reaction here, the first one produces CF2L C2. Okay, so how are we going to arrange that? So it will be C bonded to 2 chlorines, okay, and then 2 fluorines like that. Okay, so this is freon 12 plus 2, and then in the brackets I have H minus what? Not minus, H bonded to F, and then plus 2, and then I have H, which is bonded to what? To H, which is bonded to Cl. Okay, I have this. Okay, so you can see the bonds that I have here. I have some bonds that are H to C. Okay, I have some bonds that are chlorine to chlorine, and then I have bonds that are F to F, Okay, I have bonds from H to F. I have bonds from H to Cl. Okay, and we can also see them here. I have bonds C to F. So we need to know the bond energies of all those bonds that I've shown. Okay, so all those bonds that I've shown have bond energies. Okay, so the bond energies, I'm going to write them. If it's a CH bond, it has 112. Okay, so you can check this at the back of your Zoom the textbook. Okay, CF bond, this one here has the value of 485. Okay, CL, it has 328. And then we also have HCl. Okay, so this bond has a 431. We can also put HF bond. Okay, this bond has a 565. Okay, then we have C to Cl. Okay, Cl to Cl. This bond has 243. Okay, and then the last one is F to F. So F to F has 140, 154. So these are the bond energies that we're going to use. Okay, so from the first one here, I can see that I have 4Cl, CH bonds. Okay, I have this CH bond, I have this CH bond, I have this CH bond, and I have that CH bond. So I have 4 of them. Okay, so here where I had this bond, I'm going to write this. Okay, I'm just going to write 4, and then I write CH bond. Okay, and then plus, I still have plus 2 CL. Okay, so I'm going to erase this red part. Okay, and then I'm going to say plus 2, and then here we have F to F. Okay, and then that side we have the products here. So I'm going to come back to the products later. Okay, let's find the energy of the reactant. So the energy of the reactant will be 4 multiplied by the CH bond was 412 plus 2. Then the Cl to Cl bond was what? 243 plus 2. And then the FF bond was the 154. This should be a 4 there. So 154. So what is the energy of the reactants? Okay, what is the energy of the reactant? So let's add all this. So if I add 4 multiplied by 412 plus 2 multiplied by 234 plus 2 multiplied by 154. Okay, what am I going to get as the total bond energy of the reactants? I'm getting 2,442 kilojoules. Okay, so this is the total bond energy of the what? The reactants. Okay, so what about the product? Okay, so on the product side, you can see that I have CCl bond, CCl bond, CF bond, CF bond. So we have 2 of each. Okay, we have 2 CF bond and 2 Cl bond. So we are going to write this as this. Okay, so let's erase this. So we're just going to say 2, and then we have C, okay, 2F plus 2. Then we have C to Cl like that. Okay, and then these others there, we just leave them the way they are. So here it will be 2 multiplied by what is CF bond? Okay, CF bond, it's 485. So I'll put 485 there. Right, so this will be 485 plus 2. What is C to Cl? C to Cl, okay, is just 328. So 328. And then plus 2. So these 2 now. So H to F had 565. Then plus 2. And then we have H to Cl. So H to Cl was 431. Okay. So when I add all this energy here, so all this energy here will be the energy of it will be the bond energy of the products. Okay, so that one there was for the reactants. Here we are finding for the product. So for the products, when I add all this, I'm getting 3,618 kilojoules. Okay, so this one here will be the bond angles for the what? I mean, not angles, the bond energies for the products, and then this is the bond energy for the reactants. So how do we find the change in H? Okay, so change in H is equals to the total bond energy of the reactants minus the total bond energy of the what? The products. So let's find. Okay, so let's just leave the total bond energies there. Okay, so let's find. Okay. All right, so we're going to say change in H is equals to the total bond energy of the products, which is the total bond energy of the reactants, which we found to be 2,442 minus the total bond energy of the reactants, which we found to be 3,618. So when you subtract here, I'm going to get minus 1176 kilojoules. Okay, so the change in H will just be minus 1176 kilojoules. Okay, so that's it for question 10. Okay, so for those who would like the full video, okay, to this tutorial sheet, you are free to inbox me. Okay, so my number is in the description. You can inbox me on WhatsApp, and then you can register with our institution. Okay, so our tuitions are just 150. Okay, 150 per course per month, and they are all 9 so that you can access them from anywhere. Okay, anytime you get to learn at your own pace. Okay, so our tuitions are 150 per month. Okay, so those who want to register with us, please, you can find the number in the description, okay, of this video, so that you register, and then I'll be able to give you access to the full solutions. All right, so thank you so much for watching. Please like and subscribe, okay, to this channel for more videos.